In this video, we are gonna try to understand the logarithmic function y equals log of x to the base a, and we are gonna understand it as an inverse of the exponential function y equals a to the power x. So we'll try to understand all of these terms. What does the inverse mean, and what does the inverse of an exponential function mean? Okay, we'll go into the detail of all of these things. So what's an example of an exponential function? So y equals 2 to the power x. This is an example. Y equals 10 to the power x. This is an example of an exponential function. Y equals, say, 1 over 3 to the power x. So some constant to the power x, that makes an exponential function. So the inverse of such functions are logarithmic functions. So concretely, you know, a logarithmic function can look like y equals log of x to the base of, say, 2, right? Or y equals log of x to the base of 10. So these are logarithmic functions. These are exponential functions, and they are inverse of each other in a certain very specific way, and we are going to understand exactly what that means. Okay, so before we look at the inverse of exponential functions, let's look at the inverse of something much simpler than an exponential function. We are going to look at the inverse of a function like this, a simple function like x to the power of 3, right? This is not an exponential function, it's a polynomial function. In particular, it's a cubic function, it's x cubed, right? It's a much simpler function, and we are going to try to understand, okay, what does the inverse of this function look like, and we'll apply the same method to understand the inverse of some of these exponential functions. So let's understand the inverse of this function. So we have our function y equals x to the power 3. Okay, so one way to understand this function is, let's just look at some values of x and find out the corresponding values of y. So let's make a table, xy table. Let's say we want to, let's pick some values for x, say -2, -1, 0, 1, and 2. Okay, so as per this function, the value of y, which is y equals x to the power 3. So for when x is -2, y will be -2 to the power 3, -2 to the power 3, which is -8. Similarly, when x is -1, y will be -1 to the power 3, which is -1. When x is 0, y will be 0 to the power 3, which is 0. 1 to the power 3, which is 1. 2 to the power 3, which is 8. So x value of -2 gives us a y value of -8, and so on. So this function is basically assigning values, y values to x values in a certain way, and this function does it in this particular way. These are the example values. Let's actually make a plot of this function. We're gonna do, let's say, 1, 2, 4, 5, 6, 7, 8, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 1, 2, 3. So x equals -2, y equals -8. So where is that point? -2 and -8, we are around here. So this point exists on the graph of this function. X equal to -1, y equals to -1. So -1 is right here. 0, 0 is right here. 1 comma 1 is right here, and 2 comma 8 is right here. So the graph of this function is going to look like something like this. These are not going to be straight lines, but you get the idea. It's going to be an increasing function passing through this point, this point, this point, this point, and this point. Okay, so now let's write the inverse of this function, and first let's write it in terms of this kind of a table. So the inverse of this function, it's gonna look like this. So let's make x in my table. The inverse of the function basically swaps the y and the x values. So in our inverse of the function goes the direction opposite to the function. This function maps -2 to -8. The inverse of this function will map -8 to -2. It will map -1 to -1, 0 to 0, 1 to 1, and 8 to 2. So all that happens is the x column becomes the y column, and the y column becomes the x column. So -8, -1, 0, 1, and 8. These values get mapped to these values. So -2, -1, 0, 1, and 2. Right? This is the x column, appears as the y column here, and y column here appears as the x column here. So this is the inverse of this function. This is one way to write the inverse. Another way to write the inverse is we take this function, and this is important, we just switch x with y in this function, and that will give us the form of the inverse function. So y equals x cubed, we just switch x with y and y with x. So y gets replaced with x gets replaced with y, and we get this relationship. So this relationship between y and x is the inverse of this relationship. So in some ways this describes the inverse of this function, right? So this is not in the terms of y equals something yet, but we can write it. So you can write from this, you can write it as y equals x to the power 1/3. Right, I take the cube root on both sides, so x to the power 1/3, which is the cube root of x, and y to the power 3, its cube root is just y. So this is another form of this inverse function. Okay, so how did we get here? We started with the original function, we swapped x with y and y with x. Okay, so y equals x cubed became x equal to y cubed. This is a relationship that describes the inverse function, inverse of this function. And you can also write it as this, right? Because the cube and the cube root are in some ways the inverse of each other. So you can write this as this. Now let's try to plot this function, like, right? We can figure out what this function looks like. So -8, -2. So x is -8 and y is -2. Where does it lie on this picture? 1, 2, 3, 4, 5, 6, 7, 8. So x is -8, y is -2. So this thing lies around here. -1, -1. It is here. 0, 0, and 1, 1, and 8, 2. So 1, 2, 3, 4, 5, 6, 7, 8, 2. It's gonna be here. So this function is y equals x cube function went like this. This function is gonna go like this. Now this is interesting. If you draw the y equals x line, right, y equals x line, that line looks like this. Okay, so what you will realize is that the inverse function and the original function, they are like mirror images of each other along this line. They are reflection of each other along this line, right? This thing is reflected in this here, and this part which was under the line here is reflected in the part above the line, and same for this segment and same for this segment. In the original function it was here, its reflection in this line is here, right? So the inverse of the function is just a reflection of the original function in the y equals x line. So this is also interesting to remember, and exactly this thing will happen when we consider the inverse of the exponential function. Okay, so let's get to it. Inverse of the exponential function. Let's consider the simple exponential function y equals 2 to the power x. Okay, again let's make a table for it, table of values. Y equals 2 to the power x. Let's pick some example values of x. We can probably pick the same values. -2, we could pick any values, but let's stick with the values we picked earlier. Right, so y is 2 to the power x, so this is going to be 2 to the power of x, which is x is -2 in this line, so 2 to the power -2, which is 1/4. This 2 to the power -1, which is 1/2. 2 to the power of 0, which is 1. 2 to the power of 1, which is 2. 2 to the power of 2, which is 4, right? So that's our that's the table form of this function. Let's put it on a graph. Let's see. So 1 2 3 4, 1 2 3 4, 2 3 4, 1 2 3 4. So let's just make some points. -2 goes to 1/4, so -2 goes to 1/4. This is 1/2 and 1/4, so it's probably gonna be here. -1 goes to a half, goes to a half. 0 goes to 1, 1 goes to 2, 2 goes to 4, right? So it looks like the function is gonna look like this, and this is going to asymptote to, and the x-axis is going to be the asymptote of this function. So this is the function y equals 2 to the power x. Now let's write the inverse of this function. Okay, let's just make the table x, y, and the x column is going to become the y column, and the y column is going to become the x column, right? So x column comes also -2, -1, 0, 1, and 2, and the y column becomes the x column. So this is 1/4, 1/2, 1, 2, and 4. Okay, now let's do the same thing that we did for the x cubed function. For the x cubed function, we arrived at this relationship by swapping x and y, right? So let's do the same thing for our exponential function. So we're going to swap x and y. So y becomes an x, 2 to the power x becomes a y. So this is a relationship which describes the inverse of this function. This is the logarithm, and this is the exponential function. This is the inverse relationship of the inverse of this function, and this is called the logarithmic function. So logarithmic function is defined as this relationship, and in the case of x to the power 3, we were able to write this as y equals the cube root of x, right? So in this case, we do not have, we want to write something like y equals something of x such that, it represents this relationship. But the cube root does not work, right? Cube root is the inverse of the cube. So what is the inverse of this exponential function? Well, we have to introduce a new notation. So log, this is the notation we introduce. Log to the base ax. This is the logarithmic function, and this is defined to be same as this relationship. So whenever we have this relationship, it really means that we have this relationship. So this is sort of the definition of the logarithmic function. What is the definition of the logarithmic function? What does it mean? It means this. Anytime you want to understand what this is, you transform it into this form, and that's what it means. You already know what exponentiation means, 2 to the power y. If you know that, then you understand what this is. So this is this. By definition, these two are equivalent. Okay, so this is the logarithmic function. We started with the exponential function. Its inverse can be written in two forms. This is called the exponential form of the logarithmic function. This is the exponential form, and this is the logarithmic form. Of the exponential of this exponential function. Okay, so actually a here is 2. So the base is this number that we'll write under the log. This is called the base of this function, and in this relationship the base is going to be 2 because the constant here was 2. So again, if we plot this, it's gonna look like this, and the same relationship is gonna hold. We draw the y equals x line, okay, and the inverse of this function is gonna be a mirror image of this line, this curve in this line. So it's gonna look like this. It goes like this. This thing is gonna go like this. So the mirror image of this point is this, so it's gonna cross here, and then it's gonna go like this. No, it's not gonna go down, but it's gonna go like this. I'm gonna keep increasing. So this is the whole picture. This is the whole picture of the logarithmic function. We start with the exponential function. We consider its x and y values. We consider its inverse. The inverse is just switching y. If the function maps this to this, the inverse maps this to this. So x becomes y and y becomes x. And we do the same thing in its equation. And we introduce some new notation to really mean this thing. This and this are equivalent, and this is the basic relationship between the exponentiation and the logarithm. Okay, so let's write this in a more general form. So x to the power x equals e to the power y. This is same as y equals log of x with the base of a. These two are the same. Okay, now let's use this relationship to calculate. Suppose we want to calculate log of 8 to the base 2, for example. Okay, how do we calculate this? Say this is y. I want to calculate this. Okay, so how do I calculate this? What is the log of 8 to the base 2? Well, we use this understanding. This thing means that, you know, x is what is x here? X is 8 here, right? We are given this form, y equals log of 8 base 2, x base 2. So a is really 2 and x is 8. So we are given, so what will this form look like? X is 8, a is 2, and we do not know y, right? So the way to read this equation is, y is that number such that if 2 is raised to that number, we get 8. So what is 8? Can I write 8 as 2 to the power something? Yes, 8 is 2 to the power 3. So 8, so 8 is 2 to the power 3, so I can write 2 to the power 3 is 2 to the power y. So y is basically going to be 3. So log of 8 to the base of 2 is actually 3. See how we calculated this log, right? We went back to this relationship. We were given this form. We went back to this form to get 8 equals 2 to the power y, and then we realized, okay, y is, we can find y by thinking what is it that we can raise 2 to the power of such that we get 8. So 8 is to the power of 3, and we equated that with 2 to the power y, and that gave us y equals 3. This is how we find the value of any log, by going back to this relationship. Let's understand a couple more things. When the base is greater than 1, the exponential function is an increasing function like this, and the log function is also going to be an increasing function. Okay, when a is less than 1, a has to be positive for any of this to make sense. So a has to be uh, a has to be greater than 0, and a cannot be 1. So a can be any number between 0 and 1, or it can be any number which is strictly greater than 1. It cannot be equal to 1. Okay, so when a is greater than 1, the exponential and its inverse, the log function, they are both increasing functions. And as x increases, a to the power x increases, and log of x also increases. When a is less than 1, both of these are decreasing functions. So this is the exponential function, and this is the corresponding log function. Okay, and they are basically mirror images of each other, here and also here. So the asymptote of the exponential function here, the the x-axis is the asymptote of the exponential function. Because of the mirror image, we get that the y-axis is the asymptote of the log function. Here also the same thing happens. X-axis is the asymptote of the exponential function. Well, on the inverse case, the y-axis becomes the asymptote of the x function. So everything basically switches. The domain of the exponential function is minus infinity to plus infinity. That domain becomes the range of the log function. So the range of the log function is minus infinity to plus infinity. The range of the exponential function is the positive side, right? All the positive y's. So the domain of the log function will be all the positive values of x. So everything switches. The range of this is the domain of this, the domain of this is the range of this. Everything just uh, is very very symmetric and opposite, and all of that is in here.